Hi, I'm Doğa from MIT CSAIL, and today I will present GID, a method for identifying 3D prints using slicing parameters. Let me start with our motivation. For many years, tags have been used in many applications in HCI, and they're everywhere in our lives. As the simplest example, we are surrounded by barcodes and QR codes in our day-to-day. And these can be integrated into 3D objects as well. In the case of QR codes, they can be embossed onto a 3D surface. Or in the case of barcodes, they can be projected onto 3D shapes. While these approaches have enabled tags in 3D, they may have one issue. They are visible to the human eye. For this reason, researchers have come up with ways to hide them. These methods either require the use of larger expensive scanning equipment or specialized printing materials. For example, AirCode uses a camera and projector setup to detect gaps beneath the object surface. Infrastructs uses a terahertz scanner to detect even deeper holes. LearCode uses near-infrared dyes and a modified SLA printer to have hidden barcodes. These issues limit how 3D tags can be used today, as we either have to live with visible tags or have complicated equipment to scan subtler tags. With GID, our goal is to have unobtrusive tags that are easy to fabricate and that can be detected using low-cost scanning equipment. And the thing is, we actually do not create these tags. They're already there. GID uses the patterns that are already created by the regular 3D printing process. As you see here, when you 3D print an object, it inherently has distinct features due to the path the printer lays down. And if we have multiple copies that each have a different path layout, as you see here, we can distinguish them. Now, let's talk about what determines how these lines are printed. Before a model is sent to a 3D printer, the user has to convert it into machine instructions, which is called a G-code file. This process, called slicing, is done by using a software tool called a slicer. The slicer software takes as input various parameters, such as the line angle and width, and outputs a G-code file for the printer. Now, if we manipulate these parameters for each of these copies we want to have, they will each have a unique surface texture, as you see on the right-hand side. By taking a picture of the final prints and using image processing techniques, we can distinguish them. Thus, we meet our goals, which were to have unobtrusive tags that can be simply fabricated with an off-the-shelf 3D printer and scanned using accessible equipment, such as a mobile phone camera. Now, let's talk about the GID pipeline, consisting of two steps: tagging and identifying. We will use an example where we will create a set of 40 unique key covers for our research group. At the end of the semester, when lab members depart, we often forget to write down who has returned their keys. Using GID, we can quickly identify whom the previously returned keys belong to. Let's start with the first step, tagging. We first load the 3D model of the key cover by dragging it onto the canvas. We enter the number of instances we want, in this case 40, select mobile phone as the desired detection method, and click Generate Previews, which slices each instance with a unique set of slicing settings and shows the results. Here you see the differences in slicing settings, for example, in the line angles. We can now enter a label in the form of a text, an image, or a URL next to the preview of each instance. Since we want to give each key cover the name of one of our lab members, we enter one name per instance. We do this for 40 members and finally click Export. Upon clicking the Export button, each instance's G-code file is saved, as well as a dictionary file which stores the labels. We can now send the G-code files to our printer. Next, the second step, identifying. As you see, although the printed keys look the same at first glance, they have differences in their print paths. We first launch the GID mobile app and select the model we would like to scan from the object library. The app then helps us align the camera image with the object by showing the target and the detectlet outlines, similar to how chat caching or document scanning apps work. When the outlines are aligned in the zoom-in-the-loop setting, the app automatically captures and processes the image. After identifying the texture, it retrieves the user-assigned label and shows it on the screen. We check off the lab members who returned their keys and send a reminder to everyone else. In the previous scenario, we talked about how we can detect textures on the object surface. GID can also sense the interior of objects by adding a light source to the detection setup. Because of the translucent nature of regular PLA filaments, shining light on the prints reveals their infill. As you see here, we can distinguish between different infill patterns. For infill detection, we use a stationary setup with an integrated light source. As you see, we can distinguish between different instances of the same 3D model that otherwise look similar. Now, one important question we need to answer is, how many instances can we distinguish between using this technique? Before I dive into the details, here I would like to show the final results briefly. We can have 204 instances using a camera, and more than 17,000 instances if we use both a camera and a light. To come to these results, we need to look into two sub-questions. First, which 3D printing parameters can we manipulate at all? Let's start with the surface-related parameters. For the base surface, we can vary the line angle and the line width. For the side surface, we can vary the layer angles by reorienting the object and the layer height. For the infill, we can vary the angle, the width, and the pattern. Here is an overview again of all of these parameters. Now, let's answer the second sub-question, which is, per parameter, how many variations can we detect with a phone camera? To figure this out, we tested hundreds of copies that we printed with different settings. I had already shown you the results briefly, as you see here. Now, let's talk about where these numbers came from. For example, 204 for the base pattern. In our experiments, we determined that two baseline angles can be distinguished with 100% accuracy if they have a difference of at least 5 degrees. Similarly, for baseline width, the difference has to be 0.5 millimeters for 100% accuracy. This gives us 34 and 6 values respectively. Multiplying these values, we come to a total of 204 for the base surface. A similar process was performed for other parameters. For the complete evaluation, please refer to the paper. Now, let's talk about the image processing techniques we have used. First, for the surface patterns. For this type of detection, we use an image registration and Fourier transforms, as you see in this demonstration. Secondly, for detecting the infill, we use adaptive thresholding and template matching. To detect the infill parameters, we first need to remove the traces on the surface. We do this by increasing the contrast, blurring the image, and applying adaptive thresholding to binarize the image. Now we can apply template matching to find the correct type of infill. In this case, trihexagon. We also evaluated our system under different hardware-related and environmental conditions, including different lighting conditions, filament colors, 3D printers, and camera resolutions. For the complete evaluation, please refer to our paper. Now, I would like to introduce some of our applications. First, GID is great for user identification. In this example, we have 3D printed mugs that each have a different infill, which this coffee maker can detect using a camera and a light source. After recognizing the mug and identifying its owner, the machine pours their favorite drink. GID can also be used for finding previously used print settings. This is especially useful when users want to replicate existing 3D prints. Oftentimes, we try various printing settings to see which one works best for a given model. In this case, one of these 3D prints has the best mechanical integrity, and the user wants to identify its slicing parameters. Rather than carefully writing down which settings were used for which one, the maker can retrieve this information by simply taking a picture with our app. Now, I would like to discuss some of the limitations of GID. An obvious limitation is that we need to have objects that have a rotationally asymmetric contour. Objects whose bases are rotationally symmetric are challenging because, for example, for a circle, the user would not know how to align it to take a picture. For certain shapes, the number of identifiable angles is reduced. For example, for a square base, the maximum angle goes down from 180 to 90 degrees. An interesting discussion for future work is whether GID will still apply to newer and higher resolution 3D printing technologies. For this, we looked into SLA and DLP printing, and yes, these also have their own artifacts. As you see on the left, although SLA achieves better resolutions than FDM, individual layers can still be distinct. On the right, you see how in DLP printing, the projected pattern creates rectangular voxels that cause the edges to look stepped. Further, most printing methods use infill, so the general idea of varying the infill still applies. We therefore think that our method will stay relevant. Another point to consider is that, as 3D printing improves, cameras will get better as well. Just as an example, Samsung's latest image sensor for phones has a 108 megapixel resolution. So before I conclude, let me briefly summarize. In this project, our goal was to add tagging to 3D objects that is not as visible to the human eye and does not require complex printing or scanning hardware, which we have achieved by using off-the-shelf FDM printers and regular mobile phone cameras. So thank you very much for your interest, and we invite you to read our paper. Thank you.